So the first part of the course, as you know, it's all about pushing declarative programming as far as it can go. And the reason is that when you build applications, you want them to be mostly declarative. It has enormous advantages, okay, like I said before. So today, I'm going to talk about algorithms, how to design efficient declarative algorithms. And we're going to see some very interesting and clever techniques. And in order to explain that, I need first to introduce some concepts about algorithms, because we're going to look at different kinds of algorithms. So the first thing I want to explain is what is amortized versus worst case complexity. At the time. I also want to explain an interesting concept called an ephemeral versus a persistent algorithm. And I want to talk about, let's see, for lazy functions, I want to talk about incremental versus monolithic functions. Okay, this is all for understanding algorithms. So we're going to make efficient algorithms, so it's important to know what is the time complexity of these algorithms. So I'm going to explain the concept of amortized time complexity. So usually when you make an algorithm, you have operations, and each operation takes some time. Okay? So usually you have operations, and you do worst case complexity. So in the worst case complexity, you have an operation, for example, that is constant time, upper bound of 1. So n operations will take n time, okay? But for some algorithms, we cannot do that, okay? For some algorithms, we have the operations can be, sometimes they're cheap, and sometimes they're expensive. So if we do operations that are cheap, maybe they're order of 1, but the expensive ones, order of n. So that means in the worst case, it's always order n, okay? But maybe we can actually say something, if we do n operations, maybe if we do n operations, there's only very few expensive ones. Maybe the expensive ones are very few, infrequent, so that the overall time is still very low. Okay, so maybe we have this, but maybe we still have n operations order n. So maybe there's only a very few expensive ones. So if we have operations O1, O2, O3, up to On, maybe there's only one expensive one in here. Okay? And all the others are constant. So sometimes we have an expensive operation, but most of the time it's cheap. So that's almost as good as worst case order 1. It's almost as good because on average it's still order of 1. So n operations are order n, even though one operation could still be expensive. Okay? So this is called amortized complexity. So the idea is if you have n operations in general that are order of f of n time, then we can say one operation has amortized complexity of order f of n divided by n. Okay? So this is always true, but sometimes it makes a difference. Okay? Sometimes we have an algorithm where the n operations are order n, but still sometimes there's expensive operations. So this is almost as good as worst case. You see? So the expensive operations are rare. So that's the first concept. So we're going to explain sometimes it will not be possible to do worst case, but maybe we can do amortized. That's almost as good in practice. Sometimes it's not. Sometimes every operation has to be cheap. But if they're just cheap on average, maybe that's good enough. Okay, so we're going to talk about amortized complexity for some of the algorithms today. So that's the first thing that I want to explain. The next thing is a very interesting concept called ephemeral or persistent algorithms. Okay. Probably, I don't think you have seen this concept yet, but sometimes it's important. So an ephemeral algorithm only has one version of the data structure. And let me explain what it means. So let's say you have, for example, a queue data structure, okay? And let's say you have insert and delete operations, okay? So you, for example, I have Q2 is equal to insert Q1, and then I put something in the queue, and then Q3 is insert Q2, put something else in the queue. So I'm doing operations. So you can make a picture. I have Q1, I do some kind of insert operation. I have a Q2, and I can do another insert, and I have Q3. Okay, so this is reasonable for data structures. Now, in an ephemeral data structure, there's only one version. That means once you have Q3, the variable Q2 is not, the previous version does not exist anymore. Okay, that means if I do Q2 is insert Q1, if I want to do Q2 prime is insert Q1. If I want to use the same Q1 here, this doesn't work. Because once I create Q2, Q1 doesn't work anymore. There's only always one version of the data structure. Okay? So most data structures are like that. So most data structures, most algorithms that you've seen before are ephemeral. So if I have an object that implements a stack or whatever in your algorithm course, and I update the object, I change the state, the previous state doesn't exist anymore, of course. So all algorithms written with mutable state are ephemeral, okay? Which means there's always only one version of the data structure. Because once you update the data structure, of course the previous version doesn't exist anymore, okay? So you can say, sure, that's normal, right? That's what you want. But sometimes you don't, you want something more than this, okay? So sometimes you actually want more versions. And this actually is important in practice. So for example, let's say you use software development and you use something like Git, which you know. But sometimes you need more than one version. Sometimes you need more versions. Okay? So, for example, if I do Git, I do software development, I have a repository, somebody can create a branch, which is another version. Okay? So I have a repository. I can create a branch of this, and I can do modifications of this. I can create another branch. So now I have two versions, and I can independently modify, and both versions are created from the original one. So Git is actually smarter than this idea. Git is not ephemeral. We say that it's persistent. So the idea is that you can have multiple versions of data structures. So the data structure will be persistent, where we can have multiple versions. So in the queue, for example, I can do Q2 is insert Q1A, but I can do Q2 prime is insert Q1B, and now I have two versions. Okay? But if the queue is implemented using state or in a naive way, you cannot do this. Okay? So you can make a picture. So I have here Q1. I do insert operation, and I have Q2. I can do another insert starting from the Q1, and I get Q2 prime. Now, if Q1 is an object with attributes that you update, you cannot do this, okay? There's only one version always. But here now I have two versions, and I can modify these two versions separately, and I can even have more versions. And sometimes I can merge the versions together. Sometimes it's possible to merge versions, okay, back together into one version. So Git has this, okay. Databases also can do that very often. You can have multiple versions of different data. So databases can also often have versions. Okay, in collaborative work, where more than one person edits the document, you can also have multiple versions. So if you want to do offline work, for example, on a document with no internet connection, then you have your own version, okay? So versions are sometimes important. So I'm going to show today also how to do persistent algorithms that are declarative. So this is actually a very strong point of declarative algorithms. It's actually much easier to do persistent algorithms in a declarative paradigm than in a stateful paradigm. Okay? So that's ephemeral versus persistent. And we're going to see examples. So yesterday I sent a message on the Moodle. So I have on the Moodle put in a code file with lots of the examples and explanations. So I hope you're looking at that. Okay. So what I'm going to say today is already on the Moodle in this file. So the final thing I want to say is the lazy functions, the notion of incremental versus monolithic. Okay. Incremental versus monolithic. So an incremental function, if you want part of the result, it only has to do part of the computation. Okay? That's what it means. So it's lazy. So if you want part of the result, such as the first element of a sorted list, for example, it only does part of the computation. So that means the laziness is actually reducing the amount of work you do, okay? So in the quicksort is an example of this, where it reduces a lot. It goes from n log n to n if you only want the first element. But not all functions are like that, unfortunately. Some functions, if you want the first element, it has to do everything. Okay? And these are called monolithic. So if you want part of the result, the problem is it has to do all the computation. So the laziness doesn't help. Okay? For these functions, the laziness will not help you. So the idea is that we will, if we see these functions, we try to get rid of them. Okay? When we want to make lazy, we try to make them incremental. Okay? So one of the techniques I'm going to show you is how to turn monolithic into incremental functions. So let me give you an example of a monolithic. So we saw many examples of lazy functions. Typically the incremental. So the stream functions, where you put a stream on the in and a stream on the output, they're all incremental, of course. Because if you just want one element, on the output, you only have to send in one on the input. The quicksort is also incremental. So there's lots of incremental functions. But some functions, unfortunately, are monolithic. And let me just give you one example of that, of a monolithic function. It's one that we're going to see in the examples. So here's an example of a monolithic function. It's the reverse, list reverse. Okay. So I want to reverse the elements of a list. So lazy function, reverse with an accumulator. So if L is nil, then A. Otherwise, I will do a recursive call. T H bar A, like that. And then you could call it, for example, reverse 1, 2, 3, nil. So the accumulator starts nil. Now if I want to display the first element of this is a lazy function. I want to display the first element. So I hope it only has to do part of the work, but no. Unfortunately, it has to do everything. So in order to display the 3 here, it has to do everything. Okay? So you can actually see that if you look at the computation that this thing is doing. So if I take this function and I show you how it's encoded, LAR, I have a thread, and weight needed R, and then I have the body. So this is the body of the function, which goes here. Case L of nil, then R equal A. Otherwise, then reverse T H bar A R. Okay. So this is the body, goes here. So this is the function. Now let's say I want to do browse L.1 for this thing. So it's going to compute the body here. So this will compute, it will, the L is needed. Okay, so the L is the same as the R here. Let me call this R to make it no confusion. So this R is the same as this R. So R is needed. So the width needed continues. So I execute this. So the L here is 1, 2, 3. So basically, I'm going to do, it's not nil, it's 1, 2, 3, so I'm going to do H bar T, so I'm going to do this. So this turns into reverse T, which is 2, 3, and 1 bar nil, R. Okay? So I do this. R dot 1. So I'm calling reverse here. And when I call reverse, I activate the lazy suspension. And the result is I'm calling reverse again. You see, this is another call to reverse. And this call to reverse, well, R is still needed, okay? So in this call to reverse, I will also do await needed. And R is needed, it's still needed. Once it's needed forever, okay? So that means it has to keep going. And it will keep going until eventually it binds R to 3, 2, 1. So it does everything. You see that? You can see it's monolithic because the call to reverse, when I activate the lazy suspension, it turns into another call to reverse. I don't know the first element yet. Okay? So reverse is monolithic. That's a pain, okay? That's a bummer. That's not nice. This reverse function. It's also intuitive, huh? If I want to reverse a list, 1, 2, 3, and I want to know the first element of this reverse list, the first element is going to be the last element of the original list. Huh? So it's kind of logical that I have to go all the way and get the last element. Huh? So reverse is monolithic. So that's going to be a problem for one of the examples. And we're going to use a technique, we're going to have a technique to turn this reverse into something incremental. Okay? So you can see that some functions, the laziness does not do anything, does not help you, okay? Because you need everything to get the first element. And sometimes it's very logical, huh? If I want the first element to reverse list, it's the last of the original list, huh? So that's kind of logical. Okay, so that's the third concept I'm going to introduce. And now I'm going to explain what kind of declarative paradigms we're going to use. We're going to use 3 paradigms. We're going to use, so this is it's explained in the file. So we're going to use 1 sequential functional programming with values, so no data flow variables. So this is, many languages give you this, huh? It's completely declarative. So a language like Scheme will give you this. You can even do this in Java, or Lisp gives you this. The second one is sequential functional programming with data flow variables, single assignment. This gives you some extra power. Okay, and the third one is lazy functional programming, like we saw before, but I'm going to do only the sequential version. So I'm only going to show you sequential algorithms today. Sequential. So these 3 paradigms are all declarative, and we're going to show how to do things in these algorithms. Okay? So let me first summarize what we're going to do. So we're going to build I'm going to show an example data structure, which is a queue, but in fact there's many other data structures. And in fact, if you really want to find out how these techniques work, there's a really nice book called Purely Functional Data Structures by Chris Okazaki. And this explains a really, really huge number of algorithms and how to do this, okay? So if you want to build really smart declarative programs, then you should look at this book, okay? So, but I'm going to show you, what I'm going to show you is partly from this book, and partly it's something that comes from my book also. But if you want to really be smart in doing declarative algorithms, this is a really good book, okay? I don't know, maybe you can take a look at it. So what I'm going to do is the following thing. I'm going to show you a queue data structure, so a queue abstraction. I'm going to give you some algorithms. So let me first summarize what I'm going to show you today and next week. Okay. So first I'm going to show you ephemeral algorithms. Amortized constant time and worst case constant time. And then I will show you persistent versions of the queue. Again, amortized constant time and worst case constant time. Okay. So this is the algorithms I'm going to show you. First I'll show you ephemeral ones. These are like standard, but then I show you the really strong ones with multiple versions. Persistent ones that are also efficient, and it's all declarative, okay? But it's not in the same paradigm. So this one is going to use sequential functional programming. The worst case is sequential functional programming plus the data flow variables. And these two are going to use lazy functional programming. Okay? So these two, the persistence actually comes from the laziness. Laziness can give you persistence. Okay? Whereas amortized constant time is pretty easy to get. You can do it already in a very simple paradigm. But if you want worst case constant time and you're not lazy, then you can use data flow variables. Okay? So of course, worst case persistent is also ephemeral. Ephemeral is a special case where you only have one version of it. So this is what I'm going to show you. I'm going to show you the code for all this and how you design. So if you want to design smart algorithms, then this is going to help. Okay? So that's the idea. Let me start now on this. So eventually I'm going to show you the code. Let me start now on doing things. So let me show you first I'm going to show you a naive queue in sequential functional programming. And then we go to the smart queue, also in sequential functional programming. Okay? So this is the first one. This is going to be amortized constant time ephemeral. Okay? The smart one. Whereas the naive queue is not constant time, some of the operations will be expensive. So this is just a smart programming technique. So all of this is going to be regular functional programming. Okay, so now let me show you some code. Okay, so let me do first a naive queue. The queue is going to be represented by a list, and there's going to be insert operations in the front, and the delete is going to be from the back. Okay, so that's a queue. Let me define first the helper function. Which is called but last, which takes all the elements except for the last element. So this one will L, it will return L minus last element, and X is last element. Okay. So this is your typical naive functional thing. So if the list has just one element, then X will be equal to Y, and the result will be nil. Okay, otherwise, then I will continue. Okay, so this is a function that takes the L, and it'll return L minus the last element, but it has to traverse the whole list to do that. Huh? So here's the queue. Okay, so that's a queue, right? It's very simple. But this one is not very efficient. Huh? So what's the efficiency of this one? This one is actually the naive one. So insert is constant time. But delete is not constant time. So the delete depends on the size of the queue. So if the queue has n elements, the delete would be order n. Okay. So if I insert n elements in a queue and then I delete n elements, the whole time will be order n squared. So this is very bad naive implementation, huh? It's basically order n. And if you do n operations, then the time will be n squared. You see that, huh? So this is very bad implementation. Okay, now let me make something a little more clever. Okay. Let me now do, so this is a naive one. Let me now do a smarter queue. It's still going to be functional. So we're going to make it amortized constant time now. Instead of being order n squared, if I do n operations, we're going to do a smart implementation that only takes order n. And it's still functional, okay? So how do we do that? Well, we have another representation. So we represent it as a tuple. Okay? Instead of just a list, it will be now two lists. F and R. So front list and a back, a list in the back. So how does this work? There's some space here. So the actual content of the queue, so if I have queue of FR, the content of the queue is a combination of these two. Okay? It's basically append F and reverse R. That's the content. So basically F is elements on the front of the queue, and R is the elements on the back, but reversed. Okay? So I'm not going to run this. This is just to show what the content is. Huh? So now insert and delete are very simple. Insert and delete are very simple. If I want to do insert, I insert on the front, and it's constant time. Okay, if I want to, the insert is at the end, of course, in the back. So I insert by adding to R, so it becomes QF some element XR. That's easy. So I add it in the back. So you know how a Q works, huh? I add elements in the back and I take them off on the front. And the delete is basically going to look at F. Okay? So F will be equal to X bar F1, and the new Q will be F1 R. So the delete, I remove elements from the front. That's easy, right? This is also constant time. So the insert now is constant time. Great. And the delete is constant time. Wonderful. Of course, it's not that easy. There's something missing here. So I can't really do naively only that. I have to do something else. Do you see what's missing here? I have to do something else, of course. So the point is here that let's say I insert a lot of elements. They come here, and then I want to remove an element, but they are here. They're not here yet. So I need a way of transferring elements from R to F. You see that? I need a way of going from R to F. Moving elements from R to F. And that's why it's not going to be worst case constant time, but only amortized. So these two operations are both constant time, but sometimes I have to transfer from R to F, and that will be a little bit more expensive. Okay? So that's the smart one, but let me show you the code for this. So it's exactly the same interface as before. New Q is Q nil nil. In fact, all of the Qs I'm going to show you will have exactly the same interface from the outside. And it's only the inside will be different. Okay, here's the insert function. Okay, case Q of QFR, so I'm looking at F and R. And then I will do QF X bar like this. Okay. But that's not good enough, I still have to move things. But let me first write it in the naive way, and then I'll make it work. So the delete. So it will bind X to the result. Of R, like that, same as before. Then I have to remove elements, so I will have F is equal to X bar F1, and the result will be Q F1 R. Okay? So this is not good enough, I mean, both of these are constant time, but if I do an insert of one element, then I put it here, and then let's say I want to delete the same element, I delete from F. So somehow, but the element is not in the F, it's in the R. So I have to have something that moves the R to the F. Okay? So I'm going to do a function for that. So basically, I need to add a function that moves things from R to F. So I'm going to call that function check. So that's the way Okazaki calls it. So there's a check function here. And here also there's going to be check. Oops. Okay. So you see the idea? So let me now implement check. So the check function will move from R to F. Okay? So I look at, if I have nil R, then I will move it. But I have to reverse it, huh? Because R is the elements in the back in reverse. So that's the check function. So if I have a nil, if F is nil, then, and there's an R, I will move the R to the F. So I will reverse the R, put it here, and the new R becomes nil. Okay? So the check is moving elements from R to F. And this works. This is now a complete implementation of a queue. Okay, and now we can actually run it using exactly the same interface as before. Okay. And it gives me A again, exactly the same, huh? So this is still a sequential functional program. So, but it's much smarter than the previous one. You see how clever it is? It actually has an F and an R that are separate, and sometimes it moves from R to F. So this one is amortized constant time. So for example, if I do 10 inserts, now here, then I will build 10 elements here, and then if I do 10 deletes, after that I do 10 deletes, well, the very first delete will do a check, and it will do a reverse, and it will bring all the elements into the F. And all the other deletes will take elements out, okay? Because it's not nil here, so they will do no more reverse. So only do once. So you're only doing one reverse for all 10 elements. So if you compare this to the previous one, you can see that this one is n inserts, that's order n, 10 deletes, that's order n, plus one check, which does a reverse, which is also order n. So the whole thing is n, but it's amortized, because the first delete, the very first delete, is going to be expensive, okay? Because it's going to do this reverse. You see how it works? So what do you think of that? It's clever, right? It's nice, huh? And it's still purely functional. So now we have an ephemeral amortized constant time queue. And it's still perfectly functional, standard sequential functional programming. Now this one is not persistent. The reason why it's not persistent is that if I do a bunch of inserts, and then I make a second version, and I do two versions, I do deletes in the separate versions, each version will have to do the reverse, okay? So it's not persistent, because, I mean, it will work, but it will not be constant time, if you use it in a persistent way, okay? But if you use it ephemeral, then it will be amortized constant time, okay? So what do you think of that? So I'm going to make a small break now. So that's nice, right? Okay, so let me make a small, on va faire une petite pause. Well, it turns out in a standard functional paradigm, it's not possible to do that, okay? We can make it amortized, that's as best as we can do. If you want to make it worst case constant time, you have to change the paradigm, okay? So let me show you how that works. So this is still sequential
function, pure sequential. Now we have, so this is, I call this a smarter Q, and this one will be even smarter Q, okay? So this one, I want to do now a worst case, constant time, ephemeral Q, but this one will be in sequential functional programming plus data flow variables. Then we can do it, okay? Then we can make it worst case constant time. So you can see this is already an interesting algorithm, huh? But it's still not worst case constant time. So how can we make it worst case? So this is the best, huh? If you have this, in many cases this is enough, huh? Because very often ephemeral data structures are enough. You don't always need persistent one. Huh? After that we'll talk about persistence. So in order to make it persistent, we have to introduce laziness. With laziness, we can make the data structures persistent. So you can see this will be another showing of the power of laziness. Huh? So remember last week we saw quicksort. So on the Moodle, I put a file showing exactly how the quicksort is executing. Huh? So I assume you all looked at that. You see how it's running. Then you can see exactly why. It's only doing the left recursive parts, and so it's increasing the efficiency by a lot. Huh? But that's not the only power of laziness. With laziness, we can make data abstractions persistent. Okay. So this one is not lazy yet. Lazy, of course, requires more mechanisms, so you need lazy suspensions. This is only using the single assignment variables, but this is, in many cases, good enough. So here we'll have another representation. Okay. So the representation here will be again a different one. So remember here we represent the Q as a tuple of two lists. Okay. Here we will represent the Q in an even different way. Okay, we represent the Q as also as a tuple, but a different tuple. Okay. Q is a different tuple with 3 elements. So n is the number of elements. N is number of elements in a Q. Okay. And SE is a difference list. This is a new thing. A difference list it's related to a stream, okay? The nice thing about a difference list is that you can add elements in the front and in the back, okay? And we'll see how to do this. So this is a new concept, but it's built using dataflow variables, okay? So I have to explain now difference lists. So I'm going to do that by raising the screen, okay? And then we will get our worst case constant time declarative Q. So when people say declarative programming is not efficient, people will still have this idea that functional programming is not efficient. That's completely bogus, okay? Those people are stuck in the 1980s, okay? But in fact, there's no efficiency issue really. So let me show you how difference lists work. And then I'll show you how we get our worst case constant time ephemeral Q. So I have to explain the concept of a difference list. Okay, so to explain difference list, let me first start with a regular list. So in a regular list, you have a recursive definition with this vertical bar, elements, and at the end you have a nil. Okay, so we saw this, you know very well what is a list. A difference list is another representation for this, okay? It's another representation that uses single assignment variables. So it's another representation for a list. So the list ABC nil will be represented as two lists. So a difference list represents a list using two elements, or two variables, if you want. Two elements, two parts. Let me say two parts, in two parts. So the list ABC nil will be represented as A, B, C, and then an unbound variable, L, and the second part is L. So it's represented in two parts. So you could put it in a tuple. So the first part is connecting A, B, C. And then instead of ending with nil, we ended with an unbound variable. And then the second part is the variable. Is that the same variable? Okay. So now we can manipulate to this. So if we want to add an element to the front, so let's say we have A, B, C, L, L. Let's say we want to add an element to the front, the element D, okay, D. Then the list A, B, C, L, L becomes D, A, B, C, L, L. That's very simple. You just add D to the front. Like, it's very similar to do it in a regular list. But we can also add an element to the back in constant time. So here we have A, B, C, L, L. Let's say we want to add an element to the back of this. So how do we do that? Well, we will bind L. We will say L is equal to D followed by some other variable, like M, for example, and then it becomes A, B, C, D, M, M. So you see what we're doing? This is a little bit tricky, yeah? So you have to look at it carefully. So I'm going to bind L. So I bind L, and since L is at the end, the element D comes at the end. But then the trick is we have a new unbound variable, which points to the new end of the list. You see the new end here is M. It's a little bit longer. So we change the second part of our representation. You see? You have to understand that it's like an abstraction. We have we represent a list like this in two parts. So if I add an element at the end, I'm changing both parts, in fact. But this can be done in constant time, too. So you can see that with a difference list, it's possible to add an element to the front in constant time, and an element to the back, also in constant time. Whereas for a regular list, you can only do add to the front in constant time. We do D, A, B, C, nil. But if we want to add an element to the back, the result will be this. We have to traverse all the list, the whole list. So this one will be order n, where n is the length of the list. So you see, the regular list representation, adding element to the back, is expensive. Whereas in a difference list representation, adding an element to the back is constant time. Now, the point is that this is still declarative, huh? Of course, in Java you can make linked list, and you can add elements wherever you want in the linked list. But it's not declarative. It's not functional, it's not following Church-Rosser, and if you use it in concurrency or the testing, it's much harder. This is still purely declarative, huh? So with this representation, we can add an element to the back in constant time. And with this idea, we can now build a worst case constant time ephemeral queue. Okay? Okay? You see the idea here, how it's working? Okay, so let me now again show you some code. So here, now we can actually again implement another queue with exactly the same interface. So I will start by implementing new queue. So it will be a tuple. So the first element n is the first is the number of elements, and now we have a difference list. So we have to represent an empty list in a difference list. So an empty list is like this, okay? But I have to declare L, of course. Huh? You see what we're doing here? So now we have this LL is actually an empty difference list. Huh? Instead of doing A, B, C, L, L, this part has no elements, so it's just LL. Huh? This is an empty difference list with 0 elements. Okay. Now we can implement the insert and delete with exactly the same interface as before. Okay. So let me do a case to get the elements out of the queue. NSE. Then, okay, we add an element, so n plus 1. And the insert puts the elements in the back of the queue. Insert puts the elements in the back, and delete takes them out of the front. So we have to put the element in the back here. So the back is E. So we have to do something like this. E is equal to X followed by a new back, which is E1. And then the result will be n plus 1, the S, E1. Okay, we have to declare E1. Like that, okay? You see how this is working now? SE is a difference list. So SE is like this, A, B, C, L, L. So S will be the elements, and at the end an unbound variable E. So E is the unbound variable at the end. So I want to insert here, I have to bind the end. So I bind E to X followed by a new end. So E1 is the new end. So the new Q will be n plus 1 SE1. So SE1 is the new difference list. So it's like adding element to the back. It's exactly like what you can still see on the board here. ABCLL becomes ABCDMM. So the back is now a new variable. Okay. Now the point is that this is constant time, always constant time. Okay. And now we can do delete. So delete is actually very similar code. Okay. Again, we take the elements out of the queue. So now we have to remove an element from the front. But S is the front. So S is the front. So removing from the front means that you have to take the first element. So the front is this. So S would be this. So we say S is going to be equal to, Okay, S will be equal to X followed by a new front, which has less one element. We have to bind S. Okay, it's like this, huh? If I'm doing it right. So S will be something like this, huh? A, B, C, E. Okay? If I want to remove it, this will be X, will be A, and B, C, E will be the new S, S1, huh? So this is X bar S1. So S will be equal to X bar S1. There's one element, less element, so it's n minus 1. And the new front of the difference list will be S1, huh? Which has one less element. Huh? And we have bound X. Huh? This has bound X to the first element, so to A here. So you can see also this is constant time. It's interesting, they're kind of symmetric, huh? The insert and the delete. Huh? The front and the back operations are kind of symmetric. You're binding one side or the other. Huh? But you see how it works, huh? You see how the representation, how I'm adding and removing elements. Huh? So now again we can do exactly the same example as before. So you can see again the interface is exactly the same as before. So let me compile this. Then we again just use exactly the same example as before, huh? Because the interface is the same. And now I do this. Okay, and again I see A, because it's the same Q, huh? But this one is now worst case constant time ephemeral Q. Okay? So the advantage of this over the previous one is that it's worst case. You don't have this check operation. You don't have to move elements from the R to F anymore, because the difference list representation lets you add elements on both sides, huh? So that the insert and delete will work both in constant time. Okay, so this is we get this from the unbound variables, huh? But they're still declarative because they're single assignment. Okay, so this is actually a very practical implementation. You could implement it like this in Java. Of course, it would be more lines of code, but you could do the same algorithm. The unbound variable, it's like a pointer, but you can only change it once. Okay? In order to guarantee that it's still declarative. Okay? You see that? So compare this one with the previous one. So changing the paradigm, adding something, these data flow variables, lets you do a smarter algorithm. Huh? You can see it, how it works. And this one is still declarative. Huh? Okay? So that's interesting, right? And this is one step. Huh? Later we'll show you with lazy evaluation, you can even do more, even smarter than that. You can become persistent using lazy, okay? But before showing the lazy example, I have to say something more about the difference lists. In fact, it's interesting that the difference list lets you do constant time append. Yeah, question?
In the insert, how does the X is being saved in the list?
It's because the E is the end of the difference list, and if I bind E, then X goes into there.
Okay.
And E1 is the new end, okay? I can make a picture if you want to. This is the place on the left here.
So if I have something like this, so let's say I have a list with A, E, E. Okay, so this is S. So this is a queue with one element. And now I insert B. Okay, what it will do here is it will bind E. So this E will be bound. So E will be bound to B bar E1. So this becomes A bar B bar E1. And you see I'm binding the E. And then I have a new end. It's not E anymore at the end here, it's E1 now. So you see, this is a new difference list, and this one has A and B in it. You see? So the trick is that the E is changing also. It's not the same E anymore, of course. You put E1 here. But if you look at this, it's also a difference list, but A and B in there. See how it works? It's nice, and it's constant time. But before showing you the power of laziness, I have to say something more about difference list. Difference list lets you make constant time append operation. Okay? Now that's very interesting. So whenever you build something using append, append will append two lists. Append is actually slow. Append has to traverse the first list. But using difference lists, we can make a constant time append. So I'm going to show you that now, because that's a really important idea that you can use very, very often. Okay? The constant time append. So Q shows you one use of difference list, because you can add elements on the front and the back. But you can actually do more with difference lists. You can do constant time append. So let me show you first append, okay? Append L1, L2, okay? Which combines two lists and builds a new list, and it looks like this, okay? L1 of nil, then L2, otherwise H bar T, then H bar append TL2. Okay? So this is append. This is a declarative way of combining two lists. But these lists are the regular representation. Okay? So if I have A, B nil and C, D nil, this will return A, B, C, D nil. Okay? This is a regular append. The problem of this is that it's not efficient. The execution time is order of the length of L1. So if the length of L1 is n, then the time for this will be bounded by n. It will upper bound n here. It's actually theta n if you want to be very precise. It will always traverse L1. So that's not very efficient. And when you have a big program that's building a list using append, that's not efficient. But actually using difference lists, we can do constant time append. Okay, it will be ephemeral constant time. You can only do it once. But usually that's enough. When I have a big program that's building a big list, I usually build only once the answer. Okay? So this is good enough. So if I have my L1, which is represented like this, A, B, let me call this one S, S, and L2, which is C, D, T, T. So these are two different lists for the same L1 and L2 as here. If I want to now do the append of these two, what do? It's actually very easy, but I can only do it once. Basically, I have to add L2 to the end of L1. I have to add L2 to the end of L1, and the way I do that is I have to bind S. So S is the end of L1, and this is the beginning of L2. Okay? So this is actually a variable, huh? These are, I mean, there will be, if I represent it, it'll be like this, huh? In the program, it'll be like this, where S1 is A, B, S, and T1 is C, D, T. So basically, I have to bind S to this, which is the first part of L2. So basically, I have to do S equal T1. And then the result is a new difference list, S1T. So the result is the first part of the first difference list, followed by the second part of the second one, and these two parts are bound together. Okay? So I do S is equal to T1, and I return S1T. And I have done an append. Because S1T, it's actually this. It's A, B, C, D, T, T. So this is a difference list that has all the elements in there. Okay? So you can see that using difference list, you can do constant time append. That's really useful, okay? Constant time append is really useful. And the point is it's still declarative, huh? So let me show you an example of that, of how you program with that, okay? Of course it's ephemeral, but most of the time that's enough, okay? It's only certain applications which need persistent abstractions, huh? Okay. Let me show you now an example. So the point is, with difference list, you can do constant time append, ephemeral, constant time ephemeral. So let me show an example of this, of how useful it is. So let me define a function called the flatten function, which maybe you have seen, which takes a list of lists and returns a list where there's only one list and all the sublists are disappeared. So if I have a list with some of the elements are lists, it will gather up all the elements into one top-level list. Okay? So let me show you a simple definition of flatten. Okay, let me call this list XS. So if it's nil, then nil. Otherwise, I will take an element, and if X is a list, so I'm using a built-in function now. I look at the first element of XS and the rest. This is a built-in function of the system will tell me, is this X a list? Because if it's a list, like 1, 2, then I have to append it. Okay? So the way I have to do that is I do like this. I call flatten recursively on X and on XS. Okay? Like this. Okay? And in the final case, oops, then X is not a list, and I need to add it. Okay, so this is a simple definition of flatten. You see how it works. If it's nil, I return nil. If the element X, like 1, 2, is a list, Then I call flatten recursively on x, because maybe there's lists inside there too, huh? And I call flatten, oh, so this has to be xr, so it's the bug. That, okay. And I call it on xr, and then I do append. So I do append, so this is simple, right? And it will work. But I'm calling append. Which means that if flatten is a long list, it's going to traverse this whole long list, so it's going to be slowing things down. Huh? I'm appending this to make my answer. But this flatten x is only appended once. This is used in an ephemeral way, okay? I'm not appending flatten x more than once, more than one version. I'm only appending it once. So that's an indication that you can actually use difference lists for this. So with this I can actually make a better implementation of flatten, okay? So I can make an implementation using difference lists. Oops, let me show you how it works. So I take the original code. Okay, I will try to make it as clear as I can, so I will turn it into a procedure, so you can see the result, okay? And the result will be a difference list. So a difference list is two things, huh? It's a pair of two things, so I will add two arguments. So normally there's only one result here, which is a list. But my new result is going to be a difference list. So the result will be two things. So that's why I write it like a procedure. Huh? You could also pair it. You could make a tuple. But that's kind of cumbersome, maybe. So I'm just going to add two arguments. Okay? Okay, and now I will make it a difference list. Okay? So now things will be a little bit different here, okay? First of all, if excess is nil, then I don't return nil, I return an empty difference list. But what's an empty difference list? So I'm building the difference list here. So when I call this, these two variables are unbound. But an empty difference list is one where the two variables are the same variable. So the empty difference list is just S equal E. Okay, that's empty. Okay, and now let me do the append case. So I don't do append anymore. I have these two recursive calls to flatten. Okay. I have flatten x. So let me call this one S1 E1. And flatten XR S.
Ça c'est bizarre. Ah, il faut peut-être. C'est là où on a vu? Non? Ah, curieux. Ah, un glitch dans l'univers. Glitch in the universe. Okay, so now I have these two calls to flatten. But this one will make one difference list, and this one will make another difference list. So how do I combine them? Well, I have S1 will be the result, S, E2 will be part of the result, and I have to bind E1 to S2. Okay, you see how it works? So when I append two difference lists, the end of the first one has to be bound to the beginning of the next one, and the new difference list will be the beginning of the first one and the end of the next one. Okay, so let me do that. So first of all, I can do part of it like this. Okay, but E1 and S2 is actually the same variable. But I can just use the same variable. Huh? I don't have to do E1 equal S2. They're both new variables. I can just say E1 here. Right? I have to declare E1.
So that's it, huh? This will do the append. And it's constant time. See, it's very simple, huh? And it's kind of like a snake, if you want. The way I see it is that I start from S and I end in E. So I start S, I go to E1, and then I go from E1 to E. So you can kind of see it like that, huh? I'm first taking this part, and then I'm taking this part of the difference list. Okay? So that's this part. And now we do the end. So here we have one element added to a difference list. Okay? So adding one element to a difference list is fairly easy. So the S, so it would be something like this. Okay? So the S is the beginning. So it starts with X, and then it continues with S1E. So I'm basically putting X in front of the S1. Huh? Of course, I have to declare S1 there to make it work. Like that. Huh? So this is adding one element to the front. We saw already before that this is easy. Huh? Adding one element to the front. Here we're doing an append in constant time. And here we just have an empty difference list. So these two flattens are actually doing the same thing, only the second one is going to be a lot more efficient because the appends are all constant time. Let me call this one D flatten, so there's no confusion. Okay. So here we have two flattens. So let me run them now to show you how it works. This is the original one. So for example, I can do browse, flatten 1, 2, 3, 4, 5. So this shows 1, 2, 3, 4, 5. Okay. But now let's call this one. Here we have to call it now a difference list. Huh? So the call would look a little bit different. Okay. We have to actually declare some variables, but let me do it like this first. So if we call flatten, deflatten, sorry. 1, 2, sorry, 1, 2, 3, 4, 5. And now we have SE, which is my difference list, SE. But let me now display it like a regular list. Actually, you can convert a difference list to a standard list by binding the second variable to nil. That's like appending it to nil if you want. You can bind it to nil, and then S will be a regular list. So I can do something like that. I can say E is equal to nil. Browse S. Okay. Oops. There. Well, I have to compile the first bit first. That's normal. Like that. Then I get 1, 2, 3, 4, 5 again. So the two functions are actually doing exactly the same thing. Only the second one is much more efficient. So it's pure gain. Okay, there's no, except that you have to use difference lists instead of regular lists. If you look at the code from the two, you can hide it. You could hide the difference list operations inside, because it's like a pair, it's like a tuple. But you can also just add it as two arguments. So you see the code is very similar. And if you want to calculate the complexity of this, you have to calculate how many sublists there are, okay? Each sublist here has to be appended. So here there is two sublists with 4 elements in all, which means that you will need to do 2 calls to append with this one and this one. all the sublists need to be appended. So if you have a very deeply nested flatten, okay, it's going to be very expensive with these appends, huh? Whereas in this one, it's going to be, the nesting makes no difference. In this one, it only is, the complexity only depends on the number of elements, okay? Of course, you will do a recursive call here, but you will not do an append operation, okay? You see how that works? So that's something you can do very often, okay? Okay, let me now go on. So now I have one more thing to show you, is using laziness. Okay? But let me just give you an idea of how it works, the laziness. So we won't have enough time to see the code. So this is the flatten example. Let me make some room. So we're going to see how to do an amortized constant time persistent queue. So this is actually very sophisticated, huh? A persistent queue, it's not easy to implement that in any language, okay? Because you can have many versions of this, huh? So we're going to do, the idea is going to be similar to the idea of the previous one. So remember, previously, we had Q FR, and we have to sometimes move to R, okay? From R to F. Okay, sometimes we had to move elements from R to F. So we insert in the R, we delete from the F, and when F gets empty, we move there. Okay? So we're going to use a similar idea now. So we're going to use the same idea, but we're going to make it persistent. Okay? So in the previous case it was not persistent. So let me show you an example. So let's say I have a Q, I do an insert, so Q1, I do insert, Q3, I do insert, Q4. Okay, let's say I do another insert here. This is Q4 prime. Now I have two versions. Okay? And now I do delete. Q5, and so on. So in the previous case, I had to do a reverse here, and I had to do reverse here. Okay? So this actually increases the complexity. Okay? I have to do reverse in both cases. Okay, and if I have many versions, I have to always do reverse. Whatever, huh? This also has to do reverse. So I'm doing the reverse many times here. Okay? So that's a problem. That makes it not persistent. Okay? So what's the trick? The idea is to do the reverse only once, okay? Or only once for all versions. So how do we do that? So that's actually a very subtle thing. How do we do the reverse only once? Well, the only way to do that is to put it somewhere here. So basically, we have to put the reverse early. So we have to somehow move it earlier. But we don't want to do it. So we put a reverse somewhere here. We move it earlier. But we don't execute it yet. So we move it earlier, but only execute later. So that's the idea, but I will show you next time how it really works. It's the intuition. The intuition is we move it early, but as a lazy suspension. That means it's there, but it's not executed yet. And then, once it gets executed, so it's executed here, all of them will see the same value. So I don't need to execute it more than once. All will see the same value. All will see it. See the result. And the reason is that the result is some variable that was already defined here, which will be the same in all these. So when I actually execute it in one of these versions, all of the versions will see it. So instead of executing reverse many times, I only do once. Okay? So that's the basic intuition. Okay? I'm just telling you now to give you some idea, but we don't have time to do now. So let me stop here today. So next week, we're going to see how to do amortized constant time persistent queue and more evidence of how the power of laziness. Okay?